right back in it. Any questions before as I load in? Nope. Okay. So we were, did you guys hear me talking about Antoine's equation, or did it die before then?
We heard you.
Most of it. Yeah.
Okay. So, just quick read-back, definitely Antoine's equations, one of the most convenient ways of calculating vapor pressure of a species as a function of temperature. There's a couple more ways that we can look at it. Cox charts, for those that are so inclined, but the big issue with Cox charts is it's a graph, and so you're only as accurate as your ability to read the graph. And so that's why I prefer more numerical methods like Antoine's expression. The next thing we considered was Gibbs phase rule for determining the degrees of freedom for multi-phase systems. The phase rule states that degrees of freedom is equal to 2 plus the number of components minus the number of phases. And so when you're looking at multi-phase systems, Gibbs phase rule becomes really important to be able to understand how many process variables need to be specified for that system in order to have a fully specified multi-phase system. The next thing we looked at was gas liquid systems with one condensable component. And the big kicker here was the introduction and application of Raoult's law, where we consider, the partial pressure of our substance equal to the vapor pressure of that substance, which is equal to the mole fraction times the total pressure. And so by being able to calculate the vapor pressure of our substance and our mixture and knowing the mole fraction and we can get an idea of a vapor liquid split that should be expected in a system. Also, we looked at things in terms of, when things are superheated vapor, and when we're looking at saturated vapors at the dew point. Where if it's a superheated vapor, the mole fraction times the total pressure is going to be less than that vapor pressure. But if it's saturated, these values equal, and the temperature therefore is the dew point. We also looked at relative humidity. For those types of problems. And said the relative humidity of substance was the partial pressure of a substance as a function of the vapor pressure of that substance at that temperature. And this implies that, the relative humidity is 100% at saturation. Which is a little different than percentage saturation, which, well, if we're honest, in most cases isn't nearly as widely used as relative humidity. But it's a normalization of these vapor pressures as a function of the total pressures. So we get P sub I over P sub I, P minus P sub I, divided by P sub I star over P minus P sub I star. The next thing we considered was vapor-liquid equilibrium. Involving multiple components. Where the biggest thing here is our interpretation of Raoult's law and Henry's law. Where for Raoult's law, we said our mole fraction in the vapor times total pressure was equal to the mole fraction in the liquid times our vapor pressure of that substance at the temperature. This is for, rich solutions in I. And then Henry's law when we're looking at dilute species or substances. We apply a similar approach. So, application of Raoult's law and Henry's law here allows us to consider the compositions of multi-component species in vapor-liquid equilibrium. And oftentimes what you end up with is, multiple equations, multiple unknowns that you have to solve simultaneously to get your component breakdown in these systems. We also looked briefly at TXY and PXY diagrams. So I would definitely say know how to interpret these diagrams to get information about, bubble point, dew point of mixtures in terms of, this substance boils at this temperature with this mole fraction, what should I expect to have in terms of the vapor composition that forms? And so that requires your application of these diagrams. So I would say know how to use those. Those make for good final exam questions. And the last big section that we considered was looking at liquid-liquid equilibrium. Here, I'll write it out. Where we considered, the solubility of substances. We also looked at colligative properties. And definitely, we looked at ternary phase diagrams. I would definitely expect to see a ternary phase problem on your final. So be sure you're comfortable with looking at mixtures that are in liquid-liquid equilibrium and being able to use tie lines to determine the composition of the liquid phases that form to get an idea of solving material balances involving liquid-liquid extraction. So yeah, definitely make sure you've got the ternary stuff down. So that's really the key stuff for the chapter 6, as well as really the whole class. I know I went really quick, but yeah, there is a lot of information in this course. I wish I could have gone slower, taken more time on certain concepts, did some deeper dives, worked some more examples. However, we are constrained to the number of days in the month and the necessity of getting the key concepts illustrated and identified. But if there's any questions that you have, please feel free to answer them now. I don't mind staying a little bit longer. We got started a little late and my computer crashed, so I want to make sure that if there's any big burning questions that I can go ahead and answer them now for you to, put your mind a little bit more at ease for the final.
Will there be any crystallizer problems on the exam? Like solubility?
Crystallization, there might be, yes. That kind of goes into the liquid-liquid equilibrium outside of ternary stuff. Yeah, I might give you information about looking at solubility, where it comes in at one temperature, it gets cooled to another temperature, and I'll say, okay, here's the solubility of, the liquids at these temperatures. And you should be able, with that information, being able to solve the material balance as we've illustrated in a couple of example problems in class, as well as, I believe, on the homework. But yeah, and I know it's a lot of information, and I admit, I can't, I guess, test you on everything that I would like, because then the exam would be like 12 hours long, and I think everybody would hate that. But I hope I've illustrated, at least through this lecture. I'll send an email probably here in a little bit to further remind you and kind of tell you what you should expect to see on the exam. My goal is that there are no surprises. Any other questions?
Are there any examples you would recommend, or just go back through the homeworks, lectures, and review those?
That's a good question. The homework's a good place to start because it's, things that I thought were worthwhile enough that I thought you needed practice in. My goal is always to make the exam questions a lot easier than those, but at the same time still requiring you to demonstrate the same concepts. I would say look at the homeworks, don't dwell on it too much. Look at the lecture notes and the examples that we did. It's going to be closer to what I want to see on a final. But I would say the best way to study for something like this final is, make not necessarily an equation sheet, but like a study sheet. if you take the time to kind of go through each of the sections, go through the notes, and kind of come up with, in a 3 or 4 pages, what were the, the highlights? That really helps a person study. I also think in terms of helping a person study is going through the examples, going through the homework, and then asking yourself, okay, what was the process for doing, this vapor liquid type of problem? What was the process for doing this combustion reaction type problem? And you can kind of give yourself like a playbook or, a step-by-step procedure for a lot of these problems, so that when you're in the final and the anxiety's there, you kind of have, your effort and your thoughts from before to help guide you, so that you don't see a problem and you don't immediately lock up. You can say, okay, this is like I said, this is a ternary problem. What was the steps for that? Okay, now I know I need to do this, then this, then this. I think it makes test taking a lot easier. It saves you a lot of time, and I think it makes you like a better, like I said, a more effective test taker if you can do that for yourself. And I admit it's kind of hard because you've got homework due tonight, I believe, as well as the case study. Please don't forget that's also due tonight at midnight. And so, yeah, it is a lot, I will admit, but that's why I strongly encouraged everyone to, do the case study sooner rather than later, so that you had more time available to prepare for the final. Any other questions? I will be on a little bit this afternoon to answer some questions. I know there's 1 or 2 emails that I still need to respond to in regards to the case study, so I'm going to do that now once I jump off here. But as always, just send me emails. I'll try to get, watch it a little more closely today, because I know things are due. And so if you sent me something over the weekend, I apologize if I still haven't responded. My emails got a little backlogged with some other things, but I will answer them shortly. But thank you all for, the class. I hope you enjoyed it. And if not, I hope you at least learned a little something, and that, I wish you luck getting everything completed and doing well as doing well on the final.
Yes, sir. Thank you. Have a good rest of your day.
Thank you. You too. I appreciate it. Bye, everybody. Take care.